Well, welcome to this tutorial, which is going to look at one of the uses of point clouds in Houdini. A point cloud is simply a collection of points, perhaps with associated attributes, that get saved out to disk and then reused as part of generally as part of the rendering process. And there are two ways that point clouds are used, one of which is to act as a kind of cache, which is used to speed up shading calculations. And most of the subsurface scattering shaders, for example, use this method to create efficient shaders. But that's not what we're going to be looking at in this tutorial. What we're going to be looking at here is the use of a point cloud to record some information about your scene which you wouldn't otherwise be able to access. And before we start, let's have a look at the final render that we're going to seek to achieve. As you can see, what we had there is some spheres falling off our trees, and when they hit the ground they actually affect the shading of the terrain, the ground terrain here, producing those white spots. So let's look at how we might achieve that. And I'm not going to start from the beginning, because this is a tutorial about point clouds rather than about setting up the rest of the scene, but I'll just very briefly describe what we've got here. I've created some trees using a simple set of curves, which I then copy onto some points. I then take the tree and I bring it into DOPS as a wire object, and the DOPS network is pretty simple. All we do is apply some noisy force to our trees, which causes them to sway, and if we have a look at this we can see that the trees sway as if in the wind. And what we want to do now is to take the output of this, which is here in this null, and use it as the basis for instancing our spheres and then calculating the point at which they fall off the tree and begin heading towards the ground. And then finally we're going to work out how to reflect the spheres that have landed on the ground in the shading of the ground. And that's where we're going to bring in point clouds. So the first thing I need to do is lay down a geometry object which we're going to use to store the pop network that has the falling spheres in it. So let's rename this something appropriate. I'll call it falling spheres. And the first thing I'm going to do is delete the file node, is use an object merge to bring in our tree data, and I can merge it into this object, and then I'm going to choose tree after DOPS. And the first thing I need to do is delete the points that we're not going to use to instance spheres to, and I can do that using a blast node, and I already created a group which is the points on the very tops of the trees, and I've called that tips. So we should find that listed here, and if I delete non-selected, what I'll end up with is just those points on the tops of the trees. Now the next step is to try to work out the acceleration of these points, because I'm going to use the acceleration value to decide when the spheres fall off the tops of the trees and start heading towards the ground. And that's basically the same technique that we used in the DOPS and keyframes series of tutorials. But I'm going to use a different method to calculate the acceleration this time, and I'm going to use the time shift node to achieve this. But before we go on to using the time shift, let's calculate the length of the velocity vector at the current frame, because the acceleration calculation we need to use is the length of the velocity vector at the current frame minus the length of the velocity vector at the previous frame. And we can just use this using an attribute create. And in fact, if we have a look here, we can see that the DOPS network automatically adds point velocities to all of our points. So that information already exists. I'm going to call this cvel, and we're going to give it a value of length. And these three attributes in fact have standard local variables attached to them: $vx, $vy, $vz. So that's created an attribute called cvel. Let's rename this current vel. But we need to have the velocity at the previous frame in order to be able to calculate acceleration. And so we're going to need to use the time shift to achieve that. So let's lay down a time shift node. And as you can see, it has a parameter here, frame, and this allows you to set the frame at which the network that's attached to this will be evaluated. So if I connect this together to here, and then put $f -1, what we're getting here with the display flag on this node is not the state of the network at frame 39, but the state of the network at frame 38. Now this is potentially quite an expensive calculation, because you're having to re-evaluate this entire network, not just this small one here, but everything that's being drawn in here through the object merge. You're having to re-evaluate that at the previous frame. But of course, we've actually already evaluated it at the previous frame, because by definition we've been through these frames in order to get to here, or at least we usually have. So we can use another node to make this more efficient, and that's the cache node. And what the cache node does is store a copy of the incoming geometry at a set of frames, and then this node will simply look up the previous frame in this cache if it's there, and it's only if it's not in the cache that it evaluates all of these nodes up here. And the cache node allows you to decide how many frames to cache, and by default it's frame 1 to 300, which would be fine in this case. But although we don't have much geometry here, I think we've only got 275 points, we could probably afford to cache all of those for every frame. It's good practice just to keep the frames that you need, and in our case we're not going to need anything after the current frame, and to be safe I'm going to just save the 2 previous frames and the current frame. So this should ensure that we're not re-evaluating the network every time. I now need to calculate the velocity at this previous frame, the length of the velocity vector. So let's do that by copying and pasting the velocity calculation node that we had earlier, and I'm going to rename this ovel. So we've now got an old velocity attribute and a current velocity attribute, but they're on different parts of the network, so we need to bring them together in order to use them both in a calculation. And we can do that using an attribute copy node. And what an attribute copy node does is simply transfer attributes from one set of points, in this case, to another set of points based on the point number. And since the geometry is remaining constant, the number of points is remaining constant as we go into these 2 branches of the network, that's a safe thing to do. If your number of points was varying frame by frame, then you might get unexpected results if you try an attribute copy. So we're going to copy the old vel or ovel attribute over to these points here. So I need to select other attribute, and I need to type in ovel. This should mean that what we've got here is both cvel and ovel, and then I can use a further attribute, create, to calculate the difference between those 2. and let's call this p_accel for point acceleration, and I'm going to have cvel minus. Now it's giving us an error because unfortunately we're losing, in this attribute copy here, we're losing the local variable oval. So I'm going to, instead of using the local variable, I'm going to have to use a point expression. And we can just use the previous node, attribute copy. And the value is $pt, and the attribute is oval, and we want, it's only got one value, so we want a value of 0 here in the last, in the index value. And that should ensure that we have an acceleration value. There's one more thing to do to tidy this up, which is when we used our timeshift node here, we've got $f-1, and that's potentially a bit dangerous when we get down to frame 1, because then we'll be trying to evaluate at frame 0, and we may not have information, our network may not be built to evaluate properly at frame 0, so it's always best to have a max expression so that this always evaluates to 1 or more. So the next thing I'm going to do is create a null, and I'm going to call it pointRef. And then I'm going to append a pop network. Let's dive inside, and I'm going to lay down a source pop. In this case, we're going to birth from the first context geometry, which is our incoming points. We can leave it at points ordered as the emission type. And on the birth tab, I'm going to change this so it's $ff equals 1. So this is only going to birth at the first frame. I'm going to turn off constant activation, and I'm going to put the birth rate here as $npt. $npt in the context of the source pop means the number of points in the incoming geometry, and this means that we're going to birth one particle rather, for each point in the incoming geometry. By the way, $npt in other pop nodes refers to the number of particles in the pop network, but in the source pop it means something different. It's the number of points in the incoming geometry. So this is going to give us a particle for each point in the incoming geometry. And I want to split those into the points which are still attached to the trees and the ones that are falling. The first thing I need to do is create a birth group. And this is just going to contain the points that have been born this frame. I'm not going to enable preserve group, which would simply accumulate all of the points that have been born into this birth group. So there's just the points born this frame. And then I'm going to use an attribute node to create an attribute called init. And this is going to be, and I'm going to apply it just to the birth group, and I'm going to give it a value of 1. So what's going to happen is each part of the particles are all going to be born, and they're all going to get a value of init of 1. And the next thing I'm going to do is create a group of points which are beginning to fall off the trees. And I'm going to do that using a group node. And I'm going to use an expression here to create our group. So I'm going to enable this, and I'm going to call this transition group. And let's give the group name the same by saying $os. And the formula I'm going to use, or the expression rather I'm going to use here, is going to refer back to the points in the incoming geometry. Point, I'm going to use a point expression, and I'm going to use that pointRef that we earlier created, the null, and I'm going to get attributes from this point based on the particle. And thus we need to know which particle was birthed from which point. By default, we don't get that information on our particles, but we can enable an attribute which provides us with that information here on the source pop. If I add origin attribute, that's going to give me the point number of the point from which our particle was birthed. So I can then refer to this here as our point number. So $origin, and then I'm going to refer to the p-axel value that we calculated earlier. The index is 0 because it's only a float, and I'm going to test whether that is 0. And I'm also going to only apply this when our init value is 1. And I'm also only going to apply this when the frame number is greater than, and again I'm going to use a point expression referring back to point ref origin, and I've created an attribute, and I'll explain this in a moment, called start frame. So what this is going to do is only allow the points to fall off the tree when their acceleration is less than 0, and that's essentially exactly the same thing as we were doing in the dots and keyframes tutorial. When the value of init is not 1, is 1, and where the frame number is greater than an attribute called start frame. And what I've done back here on the trees, when we created our trees and copied them around, I created a random number here between 50 and 70, 20 and 70, which ensures that all of our particles don't fall off all the trees at the same point. This allows us to stagger the particles falling off the trees by using this random number. And we've added this as a point attribute here to the points on our grid. Then we copy our trees onto that grid, and on the attribute tab of the copy node I've enabled this thing, use template point attributes, and put a star in here. This means that any point attributes set up here will be copied to all the points of the tree being copied to that point. So that's how we get our start frame, which we're referring to back here. So now I need another attribute node, and I'm going to change the value of init. But I'm only going to change the value of init for the particles that are in the transition group. So I'm going to take the value of init and I'm going to make it 0. So let me call this 0 init. So now any points that are in the transition group will have an init value of 0. The next thing to do is to create a group of those points. So that's pretty simple. I'm going to use a group node, and I'm going to call this init group. Again, $os ensures the group name is the same, and I'm going to give it a role $init equals 1. And again, I'm going to enable this. And then I'm going to use another group node to create something called free group. Again, $os. And rather than use a rule here, I'm going to use the combine tab to say that free group does not equal init group. So free group is going to contain all of the points which are not in init group. So what's going to happen is that the points are all initially going to be in init group, and then as this is evaluated when the acceleration and frame number are right, points are going to move from the init group into the transition group and thus into the free group. And we can thus use different forces to control the position and speed and so on of those two different types of particles. So the first thing I'm going to do is use a position node. And a position node allows us to set the position of a set of particles explicitly. And I'm going to set the position of the init group explicitly. And we're going to do that using, again, our point expression, referring back to point ref. And I'm going to again use $origin as the point number, and the attribute that I'm going to look at is P, which is the position of our points on the incoming geometry, and this is going to have an index of 0 because it's the X component. I'm going to copy that parameter and paste the copied expression into each of the other components, except that the Y value has to take the first index and the Z value the second index. So what this is doing is ensuring that the position of the particles in init group follows the position of the points from which they were birthed. So that means those particles will simply stick to the tops of the trees. The next thing is to create a force that's going to act on the particles that are free. So I'm going to create a force pop, and we're going to apply this just to the free group, and I'm going to give it a force of -3. This isn't quite the same as gravity, of course. I'm going to ignore the mass. It's not the same as gravity, but it's going to give a nice slow effect in the falling particles. I'm also going to add a little bit of noise. I'm going to up the amplitude of the noise to 0.2, and that should ensure that the speed and motion of our falling points varies. We need the points to collide when they hit the floor, so I'm going to need a collision pop to achieve that. And again, we're only going to apply this to the free group. That's the points that are falling. And I'm going to collide with the floor, so I need to reference my floor SOP here, which is here. And the floor is simply a box that I've divided and made the surface of slightly rough. And I need to determine what behavior happens when these points hit the floor. And what I want to happen is for them to stick on collision. And I'm going to give them a group. So what will happen when they hit the floor is that they will be stuck, they'll cease to be affected by the force, and they'll become part of this hit group. And the final thing I'm going to do, because it slightly improves the motion of the particles, is add some drag, and I'm going to give us just the basic default drag of 1. So I've tweaked the scene a little bit to increase this force and to change the expression that we use to generate the start frame attribute. And I've done that so that the particles fall a little bit faster than they would otherwise do. And the next thing I need to do is instance a sphere to each of our particles. And so I need to lay down a sphere, and I'm going to give it a small radius, 2, and I'm going to use a copy SOP to copy it to each of the particles coming out of our pop network. So that's giving us a sphere on each of the ends of the branches. And if I play, what we should see is that they wave about and then they start falling towards the ground, and then they hit the ground and stay there, stuck. The thing that I don't in fact want is for them to stay stuck to the ground. What I want to do is only instance spheres to points that have not hit the ground. And let's go back into our pop network. Here I created something called the hit group. Now in fact the hit group will allow us, if I tick preserve group, to know which particles have hit the ground. So we should see here that 5 of them are in hit group. I think that's because we need to redo our simulation. And we should now find that 214 points, almost all of the points are in hit group, so they've hit the ground. So I can go up outside the pop network, lay down a blast SOP, and delete the points in hit group. So this should mean that only the points that have not yet hit the ground will have spheres instant to them.